Hello everyone, welcome to engineering mechanics tutorials. So in this video we are going to discuss about moment of inertia. So first I would like to tell you what is moment of inertia. So already we have discussed about what is moment. That is moment of force, which is the tendency of rotation of the body due to the force acting on it. So similarly it is also similar to that, the moment of inertia. So we go further. What is moment of inertia? So first, what is the definition? I would like to tell you. So the definition is given for the moment of inertia as it is a moment of moment. Okay, already moment we know. So it is defined as a moment of moment which tries to resist the angular acceleration of a body. Okay, so it is a moment of moment, so which will be possessed by the body, and that will try to resist the angular acceleration that may caused by the body due to the action of the force. Okay, and is expressed as a product of mass or area and square of its distance from the axis of rotation. So whenever the we have already discussed, whenever the force acts on a body, so with respect to any particular point the body tries to rotate. Okay, that is called as moment. So here moment of inertia is moment of that moment. Okay, so which can be written as a product of the area and the square of the distance from the reference point or from the axis of the rotation. So that moment of inertia will try to resist the angular acceleration that can be possessed by the body during its rotation. Okay, so that is about moment of inertia. So I would like to give an expression for the moment of inertia. Okay, so for that we already know that about moment. So moment is the force into perpendicular distance from a reference point to the line of action of the force. Already we know that, but here in place of force we'll be taking mass or area. Why we'll be taking mass or area means due to the uniform thickness for plane figures, due to the uniform thickness and the homogeneous of the material, it is assumed that the force or mass is proportional to the area of the plane figure. So when we consider the uniform thickness bodies, okay, or any sections, okay, uniform thickness means we can consider sectional planes. So for those sectional planes, the force or mass can be proportional to the area of that plane. Okay, so if the moment equation can be modified according to this assumption as moment is equal to area into distance. Okay, in place of the perpendicular distance we can consider the distance with respect to axis with which we are going to find out the moment. Okay, so the moment can be written as area into distance. Okay, and now again the moment I want to write it as area into x, so I'm assuming the distance as x. Okay, so next I want to write moment of moment, which is the moment of inertia. Okay, now moment of moment itself, moment of inertia. So that moment of moment, moment is generally area into distance. So moment of moment means this area into distance into again distance will give you the moment of moment. Okay, so this moment into distance x, that is area into distance will give you the moment of moment, which can be again called as moment of inertia, or we can call it as second moment. Okay, first moment is moment only, second moment is moment of moment or moment of inertia. Okay, so now I would like to write as a into x square. Okay, that is only second moment or moment of inertia, which can be written as a into x square, product of area and the square of the distance from a reference axis with respect to which the rotation of the body takes place. Okay, so this is the equation for the moment of inertia we can represent. Okay, now so what are the units for this moment of inertia? Area into dimension, that is the length or distance square. So area dimension is meter square and the length dimension also will be meter. So meter square, again meter square means we will be getting meter per 4, or we can write it as millimeters per 4 or meters per 4. Okay, these are the units for the second moment or moment of inertia. Okay, this is the representation of the equation for the moment of inertia according to the analysis by the definition. Okay, so now again I would like to give an integration method for finding the moment of inertia. So by the same definition analysis, okay, by the analysis we have written as product of area into square of the distance. Okay, so that is only for particular small area we'll be considering. But for getting the moment of inertia for the whole body, we need to consider the integration method. So why we need to consider the integration means, directly for a particular section we cannot find out the moment of inertia. So as we have discussed while finding the center of gravity or centroid, how we have divided the body or object into different shapes. Similarly here also, while finding the moment of inertia, we need to divide the body into number of convenient shapes. Okay now, so by dividing, by considering any one of particular area, that is any one particular part with particular area, so we need to apply the moment of inertia. Okay, so for that I want to take a body, okay, with respect to the x and y axis. Okay, for our convenient I want to divide the body into number of any number of parts which need not be equidistant. Okay, according to the section shape we can divide the number of parts. So this is only assumed shape. So for that any number of parts I am taking. So in this I want to consider one particular area dA. So this part I am considering, which is having the area dA. I am assuming the area of this part as dA. Okay, and next the center distance. So we have to take the central distance from x and y axis. For that I want to take the middle point of this. Okay, middle point of this area dA. So the x distance, that means the distance from the y axis in x direction I want to assume as x, and the distance from y axis in y direction I want to assume that distance as y. Okay, so by assuming this I would like to write moment of inertia of area dA. For this particular area I want to write the moment of inertia, okay, about x axis. So which is about x axis, that is equal to, already we know that area into distance. Okay, now area into distance with respect to which axis we are finding. So area dA into distance is y. Okay, distance square. Okay, a into distance square na. So dA into y square with respect to x axis means the distance is y. So area into dA into y square will get. And similarly moment of inertia of dA, same area about y axis, is equal to, will be getting dA into x square with respect to y, the distance is x, so area into x square will be getting, that is dA into x square. Okay, so these two equations are moment of inertia about x axis, about y axis, only this particular area dA. Okay, for finding whole of this body, what we have to take, we need to consider the integral with particular limits. Okay now, so that equation can be written as total moment of inertia, total moment of inertia of the body here, not dA, please strike it out. Okay, total moment of inertia of the body about x axis is equal to integration dA into y square. Similarly total moment of inertia of the body, not dA, of the body, here at the place of dA you need to consider the body about y axis is equal to, we can write it as integration of the dA into x square. Okay, this is the representation of the equation by the integration method. Okay, now by using these two equations we can find out the moment of inertia of any particular sectional shape here. Okay, so this is the moment of inertia about x axis, moment of inertia about y axis. So finally we can represent the equation as moment of inertia about xx I suffix xx, that means which is about x axis, is equal to integral y square dA. Similarly moment of inertia about y axis, that is yy I suffix yy, is equal to integral x square dA. Okay, this is the representation for the moment of inertia for any particular body, okay, in an integral method. Okay, now ix is equal to integral y square dA, iyy is equal to integral x square dA. Okay, this is about the moment of inertia. Okay, in the next video we try to find the moment of inertia of rectangular section, that is the basic section. So by applying this integration analysis to the I sectional shape, that is, sorry, not I section, rectangle shape we will be discussing. So for that rectangle shape, how to find out the moment of inertia we will be discussing in the next video. So I hope you understand this explanation. If you still have any doubts, please feel free to give a comment to my video so that I'll try to clarify your doubts. And once again, thanks for watching my video, and please subscribe and please share my videos with your friends. Okay, and once again, thank you all.